This page illustrates one of the most significant challenges in the history of computer chip design, known as the design productivity gap. It's a problem that arose directly from the success of Moore's law, which we saw on a previous page. Let's break down this graph to understand the issue. The graph plots two different trends over time, from 1981 to 2006. The top line represents the growth in chip complexity. If you look at the left-hand vertical axis, it's labeled logic transistors per chip. This line shows how many transistors we can physically pack onto a single chip. As the note says, this is growing at a staggering rate of 58% per year. This is essentially Moore's law in action. Our manufacturing technology is getting better and better, allowing us to build chips that are exponentially more powerful. Now look at the bottom line. This represents our design productivity. The right-hand vertical axis explains this as productivity, transistors/staff month. In simple terms, this measures how many transistors a single engineer can design and integrate in 1 month. While our productivity is improving thanks to better software and tools, it's only growing at about 21% per year. So, can you see the problem here? We have two lines on a graph, and both are going up, which seems good. But the top line, representing the chip's potential complexity, is rising much, much faster than the bottom line, which represents our ability to actually design it. This growing difference between what we can build and what we can realistically design is the design gap, highlighted by that red arrow. It means that over time, it takes more engineers or more time to design a chip that takes full advantage of the available technology. The complexity of the task is simply overwhelming our ability to handle it with traditional methods. The statement at the very bottom sums it up perfectly. Complexity outpaces design productivity. This gap is the fundamental reason we needed to change how we design chips. We couldn't just keep doing things the old way. This challenge forced the industry to develop new strategies, tools, and methodologies like system-on-chip design to make designers more efficient and bridge this gap. So, the natural question becomes, how exactly do we solve this problem? What are the strategies to bridge this ever-widening gap? We'll look at the answers to that next. Having just looked at the design productivity gap, we saw that chip complexity is growing much, much faster than our ability to design them. So, this naturally leads to the crucial question on this page. How can we possibly bridge this gap? The diagram here presents the modern solution. It's not just one single trick, but a collection of powerful strategies that work together. And you can see right in the middle, the central concept that ties everything together is systems on chips, or SoCs. Let's break down the strategies that make SoCs possible and so effective. First, let's look at design abstraction. Think about building a car. You don't think about every single screw and wire individually. Instead, you think in terms of larger, more abstract components: the engine, the chassis, the transmission. Design abstraction in chip design is the exact same principle. Instead of worrying about millions of individual transistors, engineers work with larger, predefined functional blocks. This allows them to manage enormous complexity without getting lost in the details. Next is design automation. This is all about using sophisticated software tools, often called EDA or electronic design automation tools, to handle the incredibly complex and repetitive tasks. An engineer can describe the desired function of a hardware block in a high-level language, and the automation tool can translate or synthesize that description into a detailed layout of transistors and wires. It's a huge productivity multiplier, much like how a compiler turns software code into machine instructions. Then we have fast prototyping. Before you commit to the massive expense of manufacturing a chip, you need to be very confident that your design is correct. Fast prototyping allows designers to create a working model of their chip, often using a reconfigurable hardware platform like an FPGA. This is critical because it lets them test the hardware and software together, find bugs, and validate the system's performance long before the final chip is made. This logically flows into design reuse. Why should every design team reinvent a USB controller or a memory interface from scratch? These are complex but standard components. Design reuse is the practice of licensing these pre-designed, pre-verified blocks. We call them intellectual property or IP cores, and integrating them into the chip. This saves a massive amount of design time and reduces risk because you're using a component that is already proven to work. Finally, all of this is supported by standard tools and hardware platforms. For design reuse to be effective, these different IP blocks from different vendors need a standard way to communicate. This means using standard bus protocols and interfaces. Likewise, using standard design tools ensures that all the parts of the ecosystem can work together smoothly. So, when you combine all these strategies, thinking at a higher level of abstraction, reusing proven IP cores, using automation tools to connect them, and verifying the whole thing with fast prototyping on standard platforms, you get the methodology for building a complete system on a chip. This approach is the fundamental answer to bridging the design productivity gap. Now, since SoCs are so central to the solution, let's move on and define exactly what they are. So, what exactly is a system-on-chip or SoC? The definition at the top tells us it's an integrated circuit that packages basic computing components into a single chip. But what does that really mean in practice? To understand this, let's look at the image of a traditional PC motherboard on the left. You can see it's a large circuit board with many different, separate components. There's a big socket where you'd put the main processor, the CPU. There are long slots for RAM memory sticks, and you have various other chips and connectors for things like your hard drive, graphics card, and USB ports. All these individual parts are spread out across the board and connected by physical wires or traces. This is a system on a board. Now, imagine taking all of those essential functions, the processor, the memory controller, the graphics unit, the input-output logic, and shrinking them down so they all fit onto one single, tiny piece of silicon. That's exactly what a system-on-chip is. The arrow in the diagram beautifully illustrates this concept. We're moving from a large, complex board to a single, highly integrated chip. If we could look inside that single-arm chip, as the diagram on the right shows, we'd find all the core components of a computer. You have the ARM cores, which are the central processing units, the brains of the operation. You have the AMBA buses, which are like a microscopic network of highways inside the chip, allowing all the different parts to communicate with each other incredibly quickly. And you have physical IPs. IP stands for intellectual property, and these are essentially pre-designed functional blocks. Think of them as ready-made components for things like USB control, video processing, or Wi-Fi connectivity that designers can integrate into their SoC. Because all of this is packed into one package, a single SoC can be a complete computer system. This is why the second point says an SoC can have most or even all of the components to power a computer. It's this amazing level of integration that makes our modern mobile devices, like smartphones and tablets, possible. They are incredibly powerful computers, but they don't need a huge motherboard because almost everything is contained within that one SoC. After seeing what a system-on-chip is from a high-level view on the last page, let's now peel back the layers and look at what's actually inside. What are the fundamental building blocks that make up an SoC? At its core, any SoC, from the simplest to the most complex, is built around three main types of components. First, you have the system master. Think of this as the brain or the manager of the entire chip. It's the component that runs the software and tells all the other parts what to do. This master is typically a microprocessor, which is a general-purpose processor like the CPU in your computer, or it could be something more specialized like a DSP, a digital signal processor, which is exceptionally good at handling mathematical calculations for things like audio or video signals. In our diagram, this is the pink box labeled System Master Processor. It sits at the top, overseeing everything. Second, you have the system peripherals. If the master is the brain, the peripherals are all the specialized tools and assistants that the brain uses to get work done. These are dedicated hardware blocks with specific functions. As you can see in the list and the diagram, this includes things like memory blocks for storing programs and data, timers to keep track of time or create delays, and various interfaces to communicate with the outside world, whether they are digital or analog. And third, how do the master and peripherals talk to each other? That's where the system bus comes in. You can imagine the bus as the nervous system or the highway system of the chip. It's a set of wires that connects all the components, allowing the system master to send commands and data to the peripherals and for the peripherals to send data back. This communication isn't random. It follows a very specific set of rules, which we call a bus protocol, to make sure information gets to the right place without any conflicts. In the diagram, this is the central gray bar that everything is connected to. The diagram shows a very simple but clear example of this structure. You have the single system master, the processor, connected via the system bus to a variety of peripherals shown in blue. Let's look at what they are. Program memory and data memory. These store the instructions the processor will execute and the data it will work with. A timer, essential for any system that needs to perform tasks at specific intervals. A DAC, which stands for Digital to Analog Converter. This is useful for producing real-world analog signals, like an audio waveform, from the digital ones and zeros inside the chip. GPIO, or General Purpose Input/Output. These are pins that can be configured by software to be either inputs, like for reading a button press, or outputs, like for turning on an LED. And a watchdog timer. This is a crucial safety feature. It's a special timer that the system must reset periodically. If the software crashes or hangs, it fails to reset the watchdog, which then automatically reboots the system. Now, it's important to remember that this diagram is a simple system. As the final point on the slide mentions, modern SoCs, like the one in your smartphone, are far more sophisticated. They often have multiple processor cores, multi-core systems, and other specialized masters like GPUs for graphics. When you have so many powerful components, a single bus isn't enough. So, they use multiple buses connected by what are called bus bridges to manage the huge amount of data flowing through the chip efficiently. We'll see an example of this more complex architecture on the very next page. After looking at the general components of a system on chip, let's dive into a more concrete example with this diagram of an ARM-based SoC. This shows how all the pieces we've talked about come together in a real-world design. At the very heart of this system, highlighted in pink, is the ARM Cortex-A9 microprocessor. This is the brain of our SoC. It executes the software instructions and manages the operations of all the other components on the chip. Now, how do all these components talk to each other? They communicate over a system of buses, which act like the chip's internal highway network. The main highway here is the ARM AMBA AXI Lite system bus. AMBA stands for Advanced Microcontroller Bus Architecture, and it's a standard developed by ARM. The AHB part means Advanced High Performance Bus. This is where the high-speed communication happens, connecting the processor to peripherals that need fast data access. On this main bus, you can see several key components connected. RAM. This is the system's main working memory, where the processor stores data and program instructions it's currently using. USRT. This stands for Universal Asynchronous Receiver Transmitter. It's a common component for serial communication, for example, connecting to a computer for debugging messages. VGA. This block would be responsible for generating video signals to drive a VGA monitor. GPIO. This stands for General Purpose Input/Output. These are pins that can be programmed as either inputs, to read from a button, for instance, or outputs, to turn on an LED. And we also have a timer and a 7-segment display controller. You might notice there's another bus on the right, the APB bus. APB stands for Advanced Peripheral Bus. This is a secondary, lower speed, and lower power bus. It's designed for peripherals that don't need the high bandwidth of the main AHB bus. Think of the AHB as a superhighway and the APB as a local side street. To connect these two buses, we have a component called the AHB to APB bus bridge. This bridge allows the main processor on the high-speed bus to communicate with the peripherals on the low-speed bus. On this APB bus, we find peripherals like a watchdog timer, which is a safety feature that can reset the system if the software crashes or hangs. More timers, another UART, and a generic block for any other low-speed APB peripheral. This hierarchical bus structure, a fast main bus and a slower peripheral bus, is a very common and efficient design pattern in SoCs. It helps balance performance with power consumption. Let's look at a few other important blocks. The clock generator provides the timing signal, the heartbeat, that synchronizes all the different parts of a chip so they work together correctly. The power management unit is crucial for controlling the chip's power consumption, enabling sleep modes to save battery life in mobile devices. You also see a DMA block, which stands for Direct Memory Access. This is a very useful helper unit. It can move large blocks of data between memory and peripherals without involving the main Cortex-A9 processor. This frees up the processor to do other important tasks, significantly improving overall system performance. Finally, on the left, we have the JTAG/serial wire interface. This is the primary way for engineers to connect to the chip to program its memory and debug the system while it's running. So, this entire diagram, with its processor, memory, various peripherals, and bus network, represents a complete system, all integrated onto a single piece of silicon, a true system-on-chip. This diagram gives us a fantastic, real-world example of what a system-on-chip looks like on the inside. This particular one is a platform SoC for Bluetooth applications. The term platform here means it's a complete hardware solution that can be used as the foundation for various Bluetooth products, like headsets or speakers. Let's break down this complex diagram into 3 main sections, as helpfully color-coded for us. First, let's look at the part in the red box labeled ARM processor. This is the brain of the entire operation. At its heart is the ARM7 TDMI core. This is a specific, well-known ARM processor that was very popular for embedded systems. It's connected to other critical components on a high-speed bus called the AHB, or Advanced High Performance Bus. Think of the AHB as the main highway inside the chip. Everything that needs to communicate quickly uses this highway. This includes the DMA controller, which stands for Direct Memory Access. The DMA is super important because it can move data between memory and peripherals without bothering the main CPU, freeing it up to do other tasks. You also see blocks for power and clock control and PLL clocks, which are essential for managing the chip's power consumption and making sure every component gets the right clock signal to operate correctly. Next, we have the application-specific logic, highlighted in the dark blue area on the right. This is what makes this SoC a Bluetooth SoC. These hardware blocks are not general purpose. They are custom designed specifically for handling Bluetooth tasks. You can see a radio I/F interface, which is the hardware that actually communicates with the outside world using radio waves. There's also a speech I/F, suggesting this chip is designed for devices that handle audio, like a Bluetooth headset. The ADC, or analog-to-digital converter, would be used to convert analog audio from a microphone into digital data that the chip can process. This specialized hardware makes the chip extremely efficient, at its intended job. Finally, at the bottom in the blue box, we have the low-speed I/O and support logic. These are the more common, general-purpose peripherals that you'd find in almost any embedded system. We have things like a watchdog timer to reset the system if it crashes, GPIO for general-purpose digital input and output, timers for precise timing, and UART for simple serial communication. Now, how do all these pieces talk to each other? You'll notice there are two main buses, the high-speed AHB we mentioned, and another one called the APB, or Advanced Peripheral Bus. The APB is a lower speed, lower power bus used for all those support peripherals at the bottom that don't need blazing fast communication. So, why have two different buses? It's all about efficiency. You don't want your high-speed processor to have to slow down to talk to a slow device like a UART. The bridge component sits between the AHB and APB, acting as a translator. It lets the high-speed components on the AHB communicate with the low-speed components on the APB without slowing the entire system down. This hierarchical bus structure is a very common and very smart design pattern in SoCs.